You can find out it's not easy. What can you play? Okay, ratio, right? So by stage, the as almost right with this remember the equal to the when the omega when the magnitude dropped compared with the magnitude to the omega equal to 0. Okay, so you increase the frequency. Okay, and then compare with the magnitude at the omega equal to 0, the 0 frequency. And when the magnitude dropped by 0.707, yeah, in other words, this magnitude, it's about 70% of the magnitude at the 0 frequency. Okay, you see, that's exactly this equation means. Okay, we define this frequency omega b to be the bandwidth of the system. Because you know why? Because we think that if the transfer function's magnitude, see, if the transfer function's magnitude dropped by the 30%, okay, see, it's the 70% of the magnitude at the 0 frequency. So this means that the magnitude is dropped by the 30%. And then we were going to say that from now on, the frequency signal will be hard to pass through the system. Okay, so we treat this as going to be a cutoff. Okay, cutoff. So any frequency that is frequency signal with a frequency that is above the bandwidth, it will be hard to pass through the system. That is the physical interpretation of the bandwidth. Okay, and according to this, according to this definition, and we actually can calculate the bandwidth omega b value for this second order system. Okay, this is for this second order system. So a second order system will always exhibit the omega b, the bandwidth value, in this. Pretty complicated, right? Pretty complicated. Okay, so you can see that for a fixed, this is a bandwidth, parameter is related to both natural frequency and the damping ratio, right? So pretty much, if you fix the natural frequency, and then it will be related to pretty much like if you have increased the zeta, if the damping ratio increase, the omega b is gonna be dropping. Okay, the omega b is gonna be dropping. Okay, okay. So this is what we defined for the transient performance in control 1. Okay, now we need to. So what we need to do here is this. One more time here to have a deep impression. We want this. Okay, we want this. In other words, you have the transient performance for this guy, for this G sub C. Okay, posted on the G sub C. Okay, but this G sub C, I mentioned many times, I don't want to get it because before I added the controller, I actually do not know the expression of the closed loop transfer function, right? I just know my closed loop transfer function must give me this kind of transient performance, but I don't have the expression of the closed loop transfer function. Instead, I have only the G of S, the open loop transfer function information. So it is very clear that we need to find out the relation between the open loop system's transfer function and the closed loop system transient performance curve index. Okay, we need to find out the relation between the open loop transfer function and the closed loop system's transient performance index. Okay, in other words, you have this kind of a second order system here, and yield this kind of a transient performance. And I want to know what kind of G of S will result in the closed loop system to behave like that. Okay? this is what I mean that to find the relation between the open loop system's transfer function and the closed loop system's transient performance index. Okay, we need to know what kind of open loop system I put it here, and it will result in a closed loop system that behaves like this. Okay, so if I know this kind of a relation, and then you know what, I will only need to play the open loop system. That is the purpose. Okay, right? Okay, so let's see how we can do that. Well, the trick is this. You see, the trick is this: is that yeah, you know what? You want the closed loop system to have a transfer function like that, and yeah, you know what? I actually can put an open loop system like this here. You can verify it. The closed loop system is going to be this, exactly equal to this transfer function. Okay. Okay. You see, with an open loop system like that, okay, and then the closed loop transfer function will be exactly equal to this. Okay. So this is the first step. So once we have this step, and then I know that okay, my job is to play this guy. Okay. Okay. You see. Then I'm gonna see, oh, you know what, how this open loop transfer function, I mean, what kind of information I can read from this open loop transfer function to implies the transient performance of this closed loop system. Okay, so then it is clear we play this, you know, open loop transfer function, but then what can you play? Okay, yeah, you know, it's a frequency response, right? Okay, frequency response. Okay, frequency response. So far, we talk about it as what? Well, yeah, you know, the most important is the stability margin, right? Stability margin. Okay, so Bode plot, Nyquist plot. Okay, so then, yeah, here the idea is that okay, then I'm gonna just draw the obtain the Bode and the Nyquist plot information of this open loop transfer function, and see how that plot is going to imply the closed loop transfer function transient. Okay, I want to see if this plot is going to give me the hint. Okay, it's going to give me the hint, and to let me predict what kind of a closed loop system's transient performance is going to be. Okay, so this is the same idea as the stability and the tracking, right? Same idea. Okay, maybe here because the transient performance complexity, and here we need to say few more words, not as straightforward like the stability and the tracking. Okay, there in that case the relation is straightforward. You can see it very clearly. Okay, but here, because of the complexity of the transient performance, the relation is not that simple. We need to do something and to extract that relation out. Okay, so yeah, the step is this: is that okay? First, I'm gonna evaluate the phase margin. Okay, see, the gain margin cannot tell me anything. Why? Because a second order system, you know that the phase of this second order system of this G of J omega will never touch the minus 180 degree, right? Because this is second order system. The phase is supposed to be between the 0 and the minus 180 degree. So you won't be able to see the phase plot to touch, you know, the minus 180 degree at the any finite frequency. Okay. You only touch it when the omega, when the frequency goes to the infinity. Okay, so the gain margin is what? It's always infinity. Okay, so it cannot tell us too much. You know, it's infinity. That's it. Okay, we cannot read any more information. So our focus here is the phase margin. Okay, then we need to calculate this phase margin. You see, from this, the calculation, you know the procedures, right? So you can calculate the phase margin of this guy to be what? The expression is here. Okay, the expression is here. Okay, No, the phase margin crossover frequency. Okay, I'm sorry. This is not a phase margin. This is a phase margin crossover frequency. Okay, okay. So you find the crossover frequency here, and then according to this frequency, then you're gonna, according to this frequency, you're gonna calculate the phase of this guy at this crossover frequency. Okay. You see, this is the unit. This is the magnitude equal to 1. So this is actually a crossover point with the unit circle, right? Okay, yeah. Recall the procedure that I summarized in for the phase margin calculation, right? So I'm following that procedure here. So you can calculate the phase of this transfer function at this frequency. It's going to be equal to this guy. Okay, it's going to be equal to this guy. Okay, so far so good. So, according to this phase, the phase margin actually can be calculated by 180 degree plus this guy. Okay, so that will be equal to the 90 degree minus 10 arctangent omega pm over 2 zeta omega n. So omega pm's expression is here, and after we substitute this omega pm in, then we find out that eventually this phase margin, it can be expressed as a arctangent 2 zeta over square root blah blah blah. I don't want to read that. Okay. The calculation is it's just tedious. This process is tedious, but it's straightforward. No trick. Okay. No trick. Straightforward. Straightforward, but tedious. Okay. But tedious. Okay. Okay. So, yeah, look at this expression. What do you find? Can someone tell me? You see, phase margin equal to this. What do you find? What do you take? Can someone tell me? If you don't reply, don't respond, and I will call the name, okay? And the first one I want to call is Ziad. Ziad, are you there? Ziad, are you there? Are you there or not? See, apparently Ziad is not there. Oh, see, Ziad, you didn't listen to my lecture, okay? I catch you. You are thinking? Okay, you know what? My question is here. My question here is that through this procedure, I calculate the phase margin of this transfer function to be like this. Now, tell me that what does it interpret from this phase margin expression? You understand the question? Anybody else? Anybody else? Hello? Hello? Anybody else? Hello? Hello? Okay. Nobody can answer? Andre? Iman? Fatima? This is the chance for you guys to show up. Okay? Abdallah? What is that? Okay? Can you answer? See, what does this expression for the phase margin means? Okay? Anybody there? I have 50, showing in the people, 50 is online. Nobody can answer the question. Okay, you see, yes, yeah, that is what I want you, that is the observation that I want you to have. Okay, now you realize that from this expression, the phase margin of this open loop systems, will depend on the zeta. Okay, then can you go further? What does zeta mean? What does the phase margin mean? What does the zeta mean? What does the phase margin mean? Can you go further? Yeah, you observe that the phase margin, well, you see, that's not what I, unfortunately, that's not the right, observation. Okay. See, what does it mean is this: the right-hand side is what? Is zeta. The left-hand side is what? Phase margin of this guy. This is what? Open loop system. Zeta is what? It's a closed loop system's damping ratio, right? Do you realize that? Zeta is the closed loop system's damping ratio, right? Okay. See, for this one, do we have the damping ratio definition? No way. You see, this one is an open loop system. We don't talk about the, you got it? Okay. Okay, Andre, you see? See, this is exactly what I wanted. I want what? I want this. You see, I mean, go back again, okay? You have to, you have to remember this very, very deeply, okay? Very, very solidly, okay? You have to remember this, okay? All we want to do is this, okay? Is this relation. We want to read the closed loop system's performance from the open loop system. Okay, in order to do that, apparently I need to establish a relation between the open loop system information, which is something that I can get from the open loop system expression, and the closed loop system's performance. And you can see that this phase margin expression, you see, this phase margin information is what we read from the open loop system, right? From this guy, right? But through this equation, we find out that this open loop system's phase margin actually is related to what? It's solely related to the damping ratio, which is a very, very good relation. Okay? In other words, what damping of the closed loop system? It actually can be read from the open loop system's phase margin. Will you agree with that? Will you agree with that? Okay. You can read the open loop system's phase margin to indicate the closed loop system's damping ratio. Okay, through this expression. Okay. Okay. So this expression is still complicated. Okay, this expression is still complicated. Of course, if you know the phase margin, you can calculate what kind of closed loop system's damping ratio is going to be. Okay, and so in order to also, you can. What does this mean is that if you pose a requirement on the closed loop damping ratio requirement, you say, okay, I want my closed loop system to have a damping ratio that is equal to 0.5. Okay, okay, equal to 0.5, right? Okay. Well, why is 0.5? That's because of the transient performance requirement, right? See, from this. The reason I need this damping ratio it's because I want the overshoot. How much is going to be the overshoot, right? Because you know the damping ratio actually determines the overshoot. So when you pose a requirement on the damping ratio, this is just like that you pose a requirement on the overshoot of the closed loop system. Okay? Okay, right? So that is why we normally characterize the closed loop system's performance by specify, okay, how much I need for the damping ratio and how much I need for the natural frequency. Okay? Okay? Okay. So now you can see that if you pose a requirement on the damping ratio, and then you know what? This equation basically tell you that the open loop system should exhibit this much phase margin. Is that nice? That is very nice. Okay? So you do not need to find the closed loop transfer function. Okay? You just need to say, okay, now I know that I just need to evaluate my open loop transfer function to see how much if the is the phase margin. Okay, if the phase margin is not equal to this guy, then I know that my controller should be added in to bring the phase margin to this level. Okay, right? Okay, so that is the point here. Okay, okay, so now. Yeah, this is the so in terms of that, yes, of course, you can always use this accurate formula to calculate. But you know, if you look at this figure, okay, this is basically shows that well, this should be the phi m. Okay, this should be the phi m, the phase margin. Okay, this is basically shows the relation between the you know, this is a formula. Okay, this is the curve that is exhibited by this formula. Okay, see when the damping ratio is 0.4 is this phase margin, 0.8 is this phase margin, 0.2 is this phase margin. This is accurate curve, but you know what? We always like you know simple. Okay, we always like simple. We actually find out that you know in this range, you know the curve can be actually approximated by this line. Okay, you see, this is exactly what we got it here. So the phase margin, it's simply equal to 100 zeta. That would be nice, right? Okay, but this is only good for an area, a certain area, and this area is what is for the damping ratio that is between 0 and 0.6. Okay, between the 0 and 0.6. And you can see that if the damping ratio goes beyond the 0.6, which is here, this is 0.6. If the damping ratio go beyond the 0.6, you know the curve becomes the slope becomes flat. Okay, so and if you still use a line, the 100 zeta to approximate it, the error generated will be bigger. So it will not be reasonable approximation. But before the 0.6, this 100 zeta actually pretty much is a good approximation, okay, of this guy, okay. 100 zeta actually is approximation of this guy, okay, of this guy, okay, okay. And the good thing is that this is so simple, okay. See, for example, let's say you want the closed loop system to have a damping ratio that is 0.5. You know what? You need to design the open loop system to have a phase margin that is 50 degree. Okay. By the way, the unit of this one is a degree. Okay. Very simple. You want a 0.5 damping ratio for the closed loop system? You better design the open loop system to have a phase margin that is 50 degree. Pretty much you will get it. Okay. Pretty much you will get it. Okay. Okay. So we solved one relation. Okay, you see, we can use the phi m, the phase margin, to indicate the closed loop system's damping ratio. Okay, which is good. Now the second one, what about natural frequency? Okay, right? What about the natural? I mean, basically, it is the bandwidth. Okay, you see, that's the reason we introduce, you know, the bandwidth performance, right? We like to use bandwidth to be posed for the closed loop system, okay? And we know that the bandwidth actually is equal to this, right? We just I just show you how this one was calculated. So you can see the bandwidth and the omega n's relation is here. So in other words, for a fixed damping ratio, when the damping ratio zeta is fixed, it's equal to a constant, then what? The bandwidth actually is proportional to the omega n. Okay, the bandwidth is proportional to the omega n. Okay, now, so because both of them are close to the performance parameter, that is not good. I need to convert them into something that I can read from the open loop systems plot. Yeah, we now recall this one, the phase margin crossover frequency. Okay, the phase margin crossover frequency. And we actually find out, you see, from this two expression, from this expression and this expression, we can actually deduce the relation between the omega pm and the bandwidth. Okay, just cancel the omega n. Okay, you see, find the omega n here and then substitute it into the second equation. Then you're gonna find out that okay, omega pm is actually equal to this one. Yeah, again, it's a nasty expression, nasty formula. Okay, very complicated. Okay, and the good thing is that I have the relation between the omega m, which is something that you can read from the open loop transfer function plot, and the closed loop system's bandwidth. Okay, so this is once again a relation between the open loop transfer function and the closed loop performance, right? Okay, and one more time, here is that this is too complicated. You can use this accurate formula to calculate this relation, no problem. Okay, for a given damping ratio, right? For a given damping ratio. Okay, but you can also use this approximation when damping ratio is between 0 and 0.6. Okay, so both formula, this one and both approximation formula works when the damping ratio is in this range. Okay, see, when the damping ratio is within this range, the omega pm and the omega b's relation is pretty much like 0.635. Okay, okay, well, that would be nice, right? See, okay, so now you can see that this relation can be realized. Okay, so let me summarize this requirement here. Say, if you want the closed loop system to have a damping ratio zeta and the bandwidth, frequency omega b, well, that is equivalent to you want a omega n. Okay, because we know the omega b and omega n, they are closely related, right? So when you specify the bandwidth requirement, you are basically specify the requirement for the natural frequency. No big deal. Okay, okay, so, and when you pose this performance expectation, you are actually pose a requirement for the omega pm and the phi m for on the open loop systems plot. Okay, see, this zeta and omega b can be realized by manipulating the open loop system to have a phase margin, to have a specific phase margin, and a specific crossover frequency. Okay, 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 okay. And the relation between these two, it's going to be summarized, it's going to be characterized in this approximation and in this approximation. For example, okay, I'll give you an example. Okay, let's say, for example, let's say I want to let's say I want a closed loop system to have a damping as a 0.4, and a bandwidth is 10 rad per second. Very high bandwidth, okay? 10 rads per second, very high bandwidth. The omega b is equal to 10 rads per second, okay? So this is the requirement for the closed loop system, okay? So I want this kind of a system, okay? And then through this two approximation, we find out that this will indicate that we're gonna need a phase margin that is about 40 degree, okay? And at what? At 10 multiply 0.635. So it's about 635 rads per second for the crossover frequency. Okay? Okay? In other words, we need an open loop system to have a phase margin 40 degree at a crossover frequency that is 6.3 rads per second. If you can do that, then you will actually achieve the closed loop system to be have a damping ratio 0.4 and the bandwidth is 10 rads per second. Okay? Okay? Okay, so then you need to go back to check your open loop system to see the system itself satisfy this margin and the crossover frequency requirement or not. If it does not satisfy, then what? Then you're gonna add a controller here to make sure the open loop system satisfy that, right? Okay, so you see that's exactly what I want to demonstrate in this slides. Okay, and yeah, here is on the Bode plot. You see, we know the relation between the Nyquist plot and the Bode plot, so we can actually indicate this requirement on the Bode plot, right? Okay, you see, so suppose you want to have a zeta, you want to have omega b, and actually this means that you need this phase margin to the crossover. Oh no, I'm sorry, this is the gain margin. Okay, this is the gain margin. You need this phase margin at this crossover frequency. Okay, this is crossover frequency. Okay, Iman, that's a very good question. Okay, actually, you know, that's a very good question. Okay, I'm glad that you asked this question. Okay, and yeah, you see, you probably realize that you know. Okay, let me erase that. Let me erase this, okay? And you know what? Let me erase this, okay? Let me explain that, okay? To answer Iman's question. And also probably this is going to be the question for a lot of other students, right? Okay. See, what happens is this. Okay, we derive this relation. We derive this approximation, this two approximation from the standard second-order system. Okay, from the standard second-order system. Okay. Okay. Now, what does this mean is that for the second-order system, we don't have any problem for the interpretation because for the second-order system, we can define the damping ratio and the natural frequency. You know that, right? Okay. Okay. Now, what about the closed loop system is high order? It's not a second order. Yeah. In this case, then the damping and the natural frequency are not well defined. Okay. If you have a high order, you know, let's say a third order or even the fourth order, even higher. Okay, then we lose the interpretation of the damping ratio and the natural frequency. Okay, you know what? Yeah, see, this is another advantage that we develop the open loop system's phase margin and the gain margin. You know, so you know in this case we're gonna take the phase margin of the open loop system as the performance requirement. Okay, why? Because you see, the phase margin actually plays the role to perform the damping ratios role. Okay, the phase margin of the open loop system actually performs the role of the closed loop system's damping. When the closed loop system does have a damping interpretation, it will indicate that the relation is straightforward. But when the closed loop system does not have a clear damping ratio definition, which is for the higher order general system case, the open loop system's phase margin still plays that kind of role. So in this sense, we are pretty much treat the phase margin and the crossover frequency as a generalized damping and the bandwidth for a general system. You got my point? Okay. You know, for example, I might have a case is that I have a high order, system. Okay. Then I'm gonna, I will not, pose the requirement on the damping ratio since I don't have the definition of the damping ratio. Instead, I will pose the performance directly on the phase margin, because you know why? Because I know that this phase margin just indicated equivalent, like the high order closed loop system should be able to exhibit this kind of damping behavior. Do you see what I mean? Okay. Okay, so in this sense, you know why we like to use the phase margin? Because the phase margin is much more generalized, performance index than the damping ratio. Okay, okay, it's much more generalized. Okay, it works for any high order system. Okay. Okay, but if you restrict your performance on the damping ratio, then basically you are only restricting to the second order system. When you have a high order system, then you don't know how to pose the performance requirement, right? Okay, so with the phase margin, and you can do it. You can proceed for the high order general system. Okay, see. That's the point, okay? I think that, even if we use the second order system as an example here to indicate this relation, yeah, you know what? I have to use an example, okay? I cannot say I have a general, transfer function open loop system here. Then what? I don't even know the expression, I don't even have this kind of expression to play. Now, what else can I say? I cannot say anything, right? So I have to use the example to exhibit this relation. But after we realize this relation, your understanding has to go beyond that, beyond this and this relation. Okay? Okay? Your understanding now is going to be like, okay, the phase margin crossover frequency is always a good indication of the closed loop system bandwidth. It doesn't matter what kind of a system you're going to have, okay? And the phase margin is always a good indication of the closed loop system's damping behavior. It doesn't matter, the closed loop system, what kind of a closed loop system you're going to have. You see what I mean? Okay? You see what I mean here? Okay? Okay. So, yeah, and this is so far so good, okay? So yeah, so like what I said, we can also read this phase margin and the crossover from the body plot. Like what I said, actually from now on, we're going to always use the body plot in the design for design. Okay, we'll always use the body plot because the body plot is easy to play when you do the design. Okay, the Nyquist plot is hard to use. The Nyquist plot is good to help us understand what happens. Okay, the Nyquist plot actually carries a better interpretation, okay, of what happens. Okay, but the body plot, it's good for design procedure. Okay, so that's why from now on we're gonna always, you know, most of the time we're gonna play with the body plot for the design. Okay, but with the aid of the Nyquist plot. Okay, so you need to understand both plot. Okay, when you find it's hard to understand something, you go to the Nyquist plot. Okay, and then come back to the body plot to do your design. Okay, so that's the relation between the two plots. Okay, that's the how which plot can be used for what. Okay, okay, so use two plots wisely. Okay, okay, yeah. Do I have to? Oh yeah. Okay, my time is here. So I will stop here first, and then we'll continue in the next class. So now I can take a couple of questions from you. Okay. I can take a couple of questions. Okay. Abdallah, you know what? The network was done yesterday. You know what? You're not losing too much time. Okay. You know. You try to finish the the assignments in time. Okay. You know what? You guys do not always try to bargain. Okay. You know, I don't like that kind of attitude. Okay. You really need this much. 1 week is a very good time for you to finish the assignment. Okay. Right now you stay home. All the time. You cannot go anywhere else. Okay. So do not compromise yourself. Okay. Okay. You can finish it. I trust you can finish it. Okay. There's no need for the extension. Abdallah, is that clear? Okay. Any other question from you guys? Any other question? Yeah. Sharp hand. If the network allows, then it will always be done. This is not a question that we should discuss anymore. Okay. Okay. Any other question? All right. Okay. If you don't have any more questions, then we're gonna stop here, and we're gonna well, next week is the break week. Oh, the week after. Okay. Yeah. Yeah. Okay. Yeah. All right. Okay. All right. I'll see you next week. Okay. Next Monday. All right.